In section 5.6, we discuss integration by substitution. Substitution is a method that will allow us to integrate, or in other words, to take the antiderivative of much more complicated expressions than we can without this method. So in this first part of the lecture, I'm not actually going to get to any examples of using the method. We're just going to build up a few pieces that we need in order to understand integration by substitution. So to that end, let y equal to f of x be a differentiable function. Since it's differentiable, that means that you can take its derivative. Its derivative is denoted f prime of x, but it could also be written as dy dx. And we haven't written it this way very often, but df dx is another way of writing it. These two ways here of writing the derivative make it appear that the derivative is the ratio of two numbers, say the number df and the number dx. But that's not at all what the derivative is. Remember, the derivative is, by definition, the limit as h goes to 0 of this complicated expression, f of x plus h minus f of x over h, provided that this limit exists. So the notation is a little misleading. It's easy to start thinking that by derivative, what we mean is a certain fraction. But this is what we mean by the derivative. Okay, that's background, that's review. Now, and in certain ways, this makes things more confusing. We are now actually going to come up with definitions for df and dx, which almost make these equations, which I just said were not true, makes them look true, but only with these new definitions. So we're now going to come up with definitions for df and dx. Before I say what the definitions are, I should say what we're going to call these. Dx is called the differential of x. Df is the differential of f. And really, I can define these things in pictures as well as I can in any other way. So let's just draw a picture. I will draw a smoothly curved function for y equals f of x. I'm going to pick a particular value of x here, and although I'm still just going to call it x instead of x0 or something like that. So suppose we have a function and we have x. If I go out a small distance here, that's what we're going to call dx. So dx is a small change in x, or a small change along the x-axis. So if we start at x and then move over here to a distance of dx, then that would make this location here x plus dx. The point on the curve directly above x, that's the point x comma f of x. And since the function f is differentiable, there's a tangent line here. And if I come up and sketch a line at height f of x, then we can come over here to x plus delta x and ask ourselves, when we moved from x over here to a distance dx above x, how far did the tangent line change? What was the change in the height of the tangent line? So there's where both the function and the tangent line were back here. And then there's this place up here where the tangent line is after we move over dx. Hopefully this looks. And that's what df is. df equals change in height of tangent line. And as you can see, when you go from x to x plus dx, the curve, the function moved up quite a bit, or just a little bit. I mean, we're really considering this as zoomed in. This is a small, I said down here small, we really could say very small. In other words, we're just imagining that this is really, really zoomed in, right? And when we zoom in, and this is a really small change in x, then the change in the height of the tangent line is approximately the change in the height of the function. So that's in the long run one of the uses for df. But for right now, all we need is that df is the change in the height of the tangent line. And here's how we get it. Here's the formula for it. df is f prime of x times dx. This must be true because now that we have these simply defined as numbers, if you look, here's the change in x along the tangent line. Here's how y changes along the tangent line. But f prime of x is the ratio of the two. It's the slope of the tangent line. So now with this df and this dx, it really is the case that f prime of x is df divided by dx. But that's because of these new definitions. So here's your differential of f. And by definition, the differential of f is f prime of x times dx, which is a small change in x values. So let's just look at some examples where we compute these things. Let f of x be x cubed plus 4x. df is equal to f prime of x, so that's 3x squared plus 4 times dx. So if I'm going to multiply this by dx, I need to put it in parentheses and say dx. I haven't specified either the value of x that we're starting at, nor have I specified how far we change in the x-axis there. But just in general, this is what the differential of f is for this function. Let's look at a couple more here. Let f of x be 1 over x, or in other words, x to the minus 1. Now what is f prime of x? Let's compute f prime of x first. It's minus x to the minus 2, so maybe we could simplify that as minus 1 over x squared. And again, if we want the differential, we apply the same formula. df is equal to f prime of x, which is minus 1 over x squared, times dx. So that would be times dx. Here's another one. Let f of x be x squared minus 7x to the 4th. Let's just go directly to df here. df is by definition f prime of x times dx. What's f prime of x? Let's bring the 4 down. And remember, since f, the original function, is a composite function, we have to use the chain rule here and multiply by the derivative of the inside function. So the derivative of the inside function is 2x minus 7. I need that in parentheses. This is f prime of x. The differential of f is f prime of x times dx. And that's really the moral for the first lecture here. What I want to close with is a slight variation in notation. We're going to bring in a variable to refer to functions. So instead of talking about f of x, we're going to talk about u. Now this is nothing new. We've frequently said let y equals f of x, but now we're going to let u equal f of x, and u is going to play a special role as we proceed through section 5.6 here. So for instance, we can have u equal to e to the 3x. And then instead of talking about df, we talk about du. What is du here? Well, it's u prime of x times dx. Same idea, just slightly different notation. So what is u prime of x here? It's the derivative of u with respect to x. Well, that's e to the 3x. Again, we have composition here. The outer function is e to a power. The inside function is the 3x. So we can call this then e to the 3x, and the derivative of the inside function is 3, and then times dx. So we might clean this up a little bit and say 3 e to the 3x dx. That's the differential of u. do one more here. Let u equal natural log of t squared plus 1. What is du in this case? The derivative of natural log is 1 over t squared plus 1. It's composition, so we have to multiply by the derivative of the inside function, which is t squared. So I was writing it correctly and thinking it incorrectly. I guess maybe I have room to do this. The derivative of t squared plus 1 is 2t. So times dt. So let me clean this up just so the answer is clear. This says 2t here, and I can put it up here in the numerator. So this is 2t over t squared plus 1 dt. All right, we will come back in the second part of the lecture in section 5.6 and start applying these differentials to certain integration problems.